incidents, but praise of the first poster is a poster where I'm honored that it's one of our own departments. I have nothing to do with that. It's the decision of the board, and it appears to be to come out as first. So I would like to introduce Remco Vellinga with the first presentation of his poster. It's titled Remimazolam Exposure Response Relationship Model for Sedation Depth Suggests Influence of its main metabolite by competitive antagonism. And I leave the floor to Remco to present his work.
Thanks for this kind introduction. Well, it's not that exotic as in Utah, but it's nice over there as well. I would love to share some results of a Remimazolam study that we did in our hospital. First, some background information. As you probably all know, Remimazolam, also known as Bifavo, is a benzodiazepine, and it has a sedative effect. Combined with an opioid, it can be used to achieve general anesthesia. It is hydrolyzed by Cas1a esterases, which are mainly present in the liver, into CNS7054, which is the main metabolite of Remimazolam. And in this presentation, we report on the exposure-response relationship for Remimazolam for depth of sedations measured by MOAs and the influence of the metabolite. So what we did, we have included 24 healthy volunteers. We stratified them by age and sex, and we've dosed them with a step up and step down scheme. We're using target-controlled infusion with effect site concentrations from 150 to 2000 nanograms per milliliter. These target concentrations were optimized on data that we have that based on interim modeling results that we have used from Payon and Schuttler and colleagues. We have collected arterial samples. We draw them at pseudo steady state after a minimum equilibration time of 25 minutes. The exposure response relationship was modeled using mixed effects proportional odds logistic regression, also known as polar, in non-men, and the depth of sedation was measured in MOAs. And this figure shows a bit how we have collected our data. We set the targets, waited for about 25 minutes or longer. First, we collected the MOAs, collected some other measurements, and then we draw a sample and raise the target again. As this figure shows, which is known as a VPC, a visual prediction check, we can see that for the lower MOAs, and first let me explain the figure. The gray boxes show the MOAs that we expected to see, and the black lines show the MOAs, or our most frequently observed MOAs. And as we can see for the lower MOAs, the higher MOAs is just where you want to see it. There is a mismatch, so it is a poor fit. Then we had the idea, could it be that there is a difference in step up and step down, which is shown in the figure in the bottom. Here, the red lines show our predictions, and the black lines show what we have observed during the study. And you can see that there is a difference between these two. And then we thought, how can this be explained? So the first thing that we got to was, could it be that the target-controlled infusion is the problem? Because as far as we know, this was the first application in DCI. The red lines show the target concentrations that we have set. The black dots show the measured concentration of Remimazolam that we saw in our volunteers. And the gray is the concentration of the main metabolite. As we can see here, our model performed quite good. But there is one other important thing that is shown in this figure, is that the ratio between the metabolite and the Remimazolam concentration is increasing over time. And for example, for the same target concentration, around 150 and 150 here, the ratio between the metabolite and the Remimazolam concentration goes from 2.9 to 63.4. And that's quite a big difference. Then we thought, it doesn't work. Then we thought, well, how can this be possible and how can we improve the fit to our model? In the left figure, that's the old situation where we have used our polar model. And then we fitted our data to a model that was proposed by Holford and Shiner that accounts for competitive interaction between two ligands at the same receptor. And that's shown in this figure. And as you already can see on this visual graph, there is quite a good improvement of the fit of a model. And going from the left figure to the right figure, decreased a delta objective function value of minus 124, which is quite impressive. So the model predicted that the metabolite is a weak agonist with a maximum effect on MOAs 15-fold lower than Remimazolam. And in the same time, the half of the maximum effect for Remimazolam is reached about 210 nanograms per milliliter, whilst for the metabolite, it's 10-fold higher, around 2,465 nanograms per milliliter. So we can conclude that there is a significant difference between step-up depth of sedation for identical effect site target concentrations between step-up and step-down. In this study, the metabolite concentrations accumulated with increasing infusion duration. And when we took into account a competitive agonism between the metabolite and Remimazolam, we actually described our data better. So that was it. Any questions?
You run around the microphone if possible, so there are